Now let's welcome Washington, who is going to tell us about formation of current vortices in graphene quantum dots, the role of molecular orbital interference.
Hello, guys. Then you can. Okay. So thank you for I'll be here, and thank you, Carlo, for this amazing conference that I like so much because I can learn a lot about different stuff like magnons and different perspective, different view. So I think that's very nice. So I'm talk a little bit about this formation of current vortex in the context of graphene quantum graphene graphene quantum dots, and I am from currently from the Institute of Theoretical Physics in São Paulo, in the São Paulo State University. And this work is make what a collaboration with the people from Iowa University and the Federal Rural of Pernambuco. So just to give you guys a little bit of motivation about this work. So this current vortex, it's already see from different perspective, different view in the context of the people that's already here in the conference. So that's a work made by Adonai and Michael. They has this a setup with defect, and they did see this type of current vortex, this type of circular current. But here they did see in the presence of spin orbital coupling. And just in another case, by Dennis and Michael and Carlos, they already did see that too in the context of topologicals, in the topological in quantum dot case. So that is the circular current in this topological case. And from even from in the perspective of magnum charge that Bill showed to us in the beginning of the conference, they did see this in this context. They did see this current, circular current, in the perspective of this in topological insulator. So I'm just trying to give you a view on when we have this effect, this phenomenon that happen in different contexts, and just why in this case of the graphene based materials, because recently from the community they has a very interest to build quantum device that and they use graphene based material. So that is just a few papers that is very recently experimental papers from a single group in Switzerland. They use these graphene based materials to make quantum dots, single electron transistors, and even recently they make in that perspective with graphene, they make this spin chain of this Heisenberg spin chain, and they use these graphene based materials to make this experimentally. So it's very nice, and but from different perspective, they are for a different group. They see too this circular current in the perspective of head currents. So and they can see this circular current too. That's very recent paper. So okay, so what? So that's just I'm trying to make you guys understand that we have this circular current in different perspective, in the magnum perspective, in the insulator perspective, in different ones. So it's to us interesting to understand that. So that's will make us to get in this particular paper that's from EUDIS. That's be here. So they did make they did make a nano flag of graphene, and they connect a leads in that nano flag, and we can see here just the flow, the flow of the current, the electron current in that perspective. And here we just have a profile that make that we have just extended states. But when we put this when we put these leads in the vertex of the nano flag, we see something very interesting, that we have the profile of quantum dots. So we have just the resonance state when you have molecular states. But more than that, we can see when we put it in this lead in a non-aligned, we has the quantum dot profile, and at the same time we see the emergence of this current vortex. But it's very important here because in that context we don't have spin orbital coupling. So we have this vortex formation, we have this circular current, but in the absence of spin vortex coupling. And because that, we make this collaboration with Alexandre I from the São Paulo State University, Dennis and Eudes from Iowa University, and Fernando Moraes from the Federal University of Pernambuco. Just that you have this just to understand what happened and understand this vortex formation. So, and we have that, and sometimes we wanted to, they see that in the context of curved quantum dots. So we have here these three different types of systems. So here we have the planar one, that is essentially hexagonal graphene nanoflag. We have that other that is a heptagonal graphene nanoflag, but they're with curved. That's pentagonal one. So we have these three different structures that you want to understand in this context. So just to give the context, we use here just a tight body model to describe this system, and we can coupling these leads, but and you use the Green's function to do that. But here is very important that you are using an orthogonal tight body model, so you have the overlap matrix, and that's important because when we want to study these curvature systems, so it's very important because usually when you have the curvature materials, the people just have the correction in the hope because the distance of the atoms. But here, when to make better with a better description, we need to put in the context of non-orthogonal states the correction goes to the overlap matrix. So if you want to study this curved material, so you need to study with this the p orbital X vector theory to correct the overlap matrix. So that's the setup that we studied. So we have the planar, and we always put the leads in the not aligned with one vertex between the leads in all the three cases, and we just have and with the Green's function we can have the density of states, the transmission, and different that the someone make to see. We have that one that's the density, the local density of current, that essentially measures the probability of current to electron goes to one side to another. So is that one we use to see the current flow, and just to measure this polarization of the current, because you already know that we have the circular current. So we use this term that we call circular current, and it's essentially when we measure the polarization of the vortex, the circular current. So if you have circular current, the polarization will be zero, but if you don't have, there will be zero. So, and that's very nice because it starts from the perspective of the planar structure. We can look to different configuration, the para configuration that we have aligned leads, and the meta configuration that we have not aligned. And when we look directly to the circular current, for the meta configuration, we see this resonance state, this resonance in the circular current. So that means in this case, we have circular current, but when we look to the to the para configuration, in principle, we don't have this resonance, so you don't have circular current. In the beginning, we chose to make this comparison because usually in the literature they say that don't has circular current in the para configuration. But if you look in very attent, that we see these two little resonance here, and when we look to that ones, we see that we has this non-trivial vortex configuration. So that's very nice, but we are just focused in the para configuration, and here we can see that. So when we have the resonance in the transmission, we essentially see this complex, but we have the circular current. But I just show that for some resonance in the transmission, we don't have the resonance and the circular current, so we don't have the vortex configuration. But for some resonance in the transmission, we have the circular current resonance, and you have this vortex that emerge. So that's very nice. But when we look to when we have the vortex configuration in the transmission resonance, we see that we have degenerate states in this context. And more than that, they are look like that, and so they are molecular states. And we see, okay, if I have molecular states that they make the contribution from the circular currents, so why not just project the system in the base of this molecular state? So that's our complex projection. But in the end of the day, what's important is we get the projection and we project the Green's function of my full system, and I have the Green function in this molecular orbital basis. So, and because we have two degenerate states in the basis of this projection, we will have a Green function in this base that are two-level Green functions. And that's very nice because one time that we have that, we can just, in this base, you can just make the back projection and get, again, the full Green function. And why that's important? Because you see, okay, so I can play with that. So we can see directly the contribution, because in this base, the Green function will be the Green function of the molecular orbital state. So I can just see the contribution directly from the density of state of these molecular states, and I can see to the contribution that's come from the off diagonal. So that's very nice because one time that I have my full spectrum, I can have my transmission, my complete transmission, but when I project, I can get the information of the single states of that to have the vortex formation. So here we see that we have just the density of state from these molecular states. And that's very nice because when we looked from the circular current from the full system, but we can also look for the contribution from the first line in my orbital case. So that's very nice because when we look to this black line that's come from the diagonal of, so that's the contribution for the circular current that's come from my state, directly from my state, that's zero, the contribution. But when we look to the off diagonal, the term that's come from like coupling term of between my states, we have this polarization. So from the first line, and you have the same in the second line of my matrix. So that means that all the contribution that's come from the circular current is come from the off diagonal term. So it's a resonance term. It's a combination that's so, and we can look directly to the density of the density of local currents, and we have the vortex when you have the full green function. But when we do the same from the term that's come from the states, we see that we don't have essentially we don't have current from the diagonal terms. So, but when we look directly from the off-diagonal terms, we has current because we know that we have polarization from these off-diagonal terms. But here we don't have the vortex configuration. We have polarization, but we don't have the vortex configuration. So, but when we just look to the combination, the contribution at some time from the off-diagonal terms, it's like assume in this current, that's enough to have the vortex configuration. So that means the effect that we have, that the circular current is come from, it's from the resonance term between the states, but the contribution does just happen if I have the off diagonal term that don't need to the directly the density of state from the diagonal. So that's come from the coupling between them. So we have essentially the electrons go one and come back and stay there in this state. So, and you can look very fast from the different structure that we have. Essentially, when you look for the central, is a little bit different. But the important stuff here, and when we get this state that has the circular current, we have this. We have for that one, we have this different profile in the transmission that has a phonon resonance here. In that one, it's a little bit difficult to see, but in that different two, it's more easily to see this phonon resonance because you have the degenerate state, you have the interference between these states, and in this state you have because that the circular current formation, and we see the same thing for these different cases. That the thing that I need to have the circular current, it's come from the coupling, the term in some sense, the coupling between these states, and from both of the cases. And we can do more than that. So in principle, we just explain, or we give a little bit description about this vortex formation, circular current. But when we make the projection, we essentially have a two-level systems, so that will be look like that. So all the two levels is coupling with the bed and has the coupling between them. And when we try to understand about the phonon resonance, we just get this model, and it's with general parameters. We see for this case, when you have this coupling, we have the phonon resonance in 0, but when we get coupling between these states, the resonance phonon is moving a little bit, but more than that, because you have the profile, asymmetric profile. When we get these asymmetric states, and with essentially the coupling between all the levels with the bath is essentially equal, it's the same, but for just one coupling with the second level with the bath, we make the more strong the others. That give us this asymmetric profile. So, and in the context of that we have for the all system, we have the 2D model, effective Hamiltonian, when we make the projection in the base of the molecular orbital states, and we know about the projection, the full form of the green matrix in this case, and we have the effective Hamiltonian for the molecular orbital states, and you have the both two, and you can just we can just look to them and just fit the parameter. You can get the coupling directly from the projection. And that's very nice, because when we have that, we see that the first level, it's the coupling, it's equal, it's the same, but from the second level, we have asymmetric coupling. And that's nice because we can, that's from directly from the structure, that is from the level, the 2D level model, with this parameter, and you see that we have an asymmetric coupling. That's enough to have the profile of the transmission with the phone resonance. So what I'm trying to say is, to get the circular current, we need to have the degenerate states. It has resonance interference, and more than that, they have effectively asymmetric coupling with the bath. So that's what we get. And just, yeah, and finish here. So just to give you a perspective, what we try to do now, it's to see this, what's happened when we put the electron-electron interaction in this circular current, because it's based on one of my work that I already did, that we use essentially this same projection to describe in the molecular states. We use the same thing, and you put directly the electron-electron interaction there, and something very nice happened. Just, I'm not explaining just about this work. It's the important thing that we see in the column diamond, a region that's purely coherence because the electron-electron interaction, and we see incoherence region. So that means that you can have that stuff, the incoherence that's come from the circular current vortex. So, but in general, it's just a perspective, but it's that. So thank you, guys. Thank you. Thanks so much.
So can you identify, it was not clear to me, whenever you have a funnel resonance, you have a discrete level coupled to a continuum. So can you identify the discrete and the continuum?
Sorry, can you repeat? I have the funny resonance here.
Yeah. So there's, did you try to derive a formula for the line shape?
No, we didn't.
Because there is a way, the funnel line shape has a well-defined formula with something called funnel parameter. That's a Q usually, but you haven't done this kind of thing.
No, we did that.
But briefly, did you think about the discrete level that is coupled to a continuum?
Yeah.
And then when we scan the energy, you have an interference that is constructive on one side and destructive on the other side. So what are the discrete level and the continuum? So
if I get correctly, you tried, if I can say what the destructive interference here is the constructive ones. Is that?
Maybe you can later.
Okay, thanks.
Any more questions?
So I'm going to ask a typical older scientist question because long baseline. So this is work that was a while ago. I'm just curious if you had stumbled across this. I think Jack Harris at Yale did some work with small gold rings and persistent currents, where he was detecting them by putting them on a cantilever and sort of measuring the induced moment from persistent current in those rings. And that seems similar to what you're seeing here. I think those rings were obviously larger because they were nanofabricated, but just curious how much, if you were aware of that work, and if so, if you could comment on the overlap.
About the magnetic response in this case?
Sure, that's an interesting direction to go.
Yeah, we are looking to that, but they has a magnetization, but we just measured how strong it is in that sense. And about the gold stuff, because usually when you have defect, we can have these circular currents. So, and of course you have this central defect that is not gold, but in the sense that has probably they has to the circular current, and so they has a magnetic response in this case. I don't know if I answered the question.
Yeah, we can talk about it in the coffee break. But no, so the experiment was they used nanolithography to make a ring of pure gold.
Okay.
And if you cool that down so that the electron wave function is coherent for the full perimeter of the ring, then it basically acts like a large molecule. You can have sort of a persistent circulation of the electrons. You can create a persistent current mode that then that circulation of the current itself shows up as like a diamagnetic response. And so in a similar way, I would think you could potentially see these circulating currents by looking for sort of a similar diamagnetic or sort of orbital driven magnetic response.
Okay, that's nice. We can talk about that, but yeah, we don't look for similar stuff, but yeah, thank you. Dennis.
So just like quick comment on Agus and Zeke's question. So the continuum here is just the leads, and the discrete energy levels are the levels from the graphene quantum dot. So it's very similar pattern that we got into, that we found in our PRL. Zeke's very interesting question. I'm not sure if I'm aware of this work, but we have been trying to push for detection of this magnetic vortex through like Biot-Savart law. If we are able to cool down, bring the Fermi energy in resonance with this vortex, there is going to be a magnetic field produced by this vortex, and in principle we can identify this experimentally. Not we, but you guys, and we could also do the, but we could also do the reverse, which is something that Washington is studying, which is whether we could use this kind of structural defects to sense magnetic fields. So, for instance, in the presence of a magnetic field, the energy levels associated to these defects and vortices, they're going to shift a bit, and then we are trying to think whether these defects are going to be, or the shift of the energy of this defect could essentially like indicate to us like what is the strength local magnetic field. So, but I would love if you could share that paper with me. I think that's very interesting. Something we started to think about it. Yeah.
So, did you calculate what the magnetic field might be? Because, you know, if you just, if the system energy is just on one of these resonances, then there's this current, and I think it is a persistent current in the same way that, was observed in the gold rings. What just by the way, as a comment, what was exceptional about the gold ring persistent current is that, gold isn't a superconductor, so it really relies on the coherence of the electron wave function around the perimeter to generate a persistent current, which is in a normal metal, which is awesome. So I think this can be viewed in a pretty similar light. I don't think this is a superconducting state. Is that right? Yeah. Maybe the question is like, what is the size of the effect? So what magnetic field is generated? That would be the first step to looking at how you might go about detecting it. I mean, one could think about NV center-based detection, but I'm skeptical that it would be easy, let's just say.
Do you want to answer?
No, yeah, because we are looking to that in this moment, so we don't have the answer to say how strong is the magnetic field, but that we are in that sense, we try to see if it makes sense or not.
Yeah, I mean, I think actually easiest way to do this would be with a microsquid. That would be my guess, or nanosquid. The ones that they have on a pulled, because this has to be a low temperature experiment, and NV centers are great sensors, but the absolute sensitivity to phi naught in a squid is the best. And it's just that they're very constrained in terms of like the conditions where they can operate, but these are the conditions. It's going to be a low temperature experiment, I assume. And so, you know, if you position a nanosquid right above one of these things, and then you bring it into resonance, then the squid can detect, you know, a smaller field than probably an NV center can. We can discuss, but that would be my guess.
Oh, okay. Thank
And
you.
just to follow up on your comment, I think our back of envelope estimate gave us something like half a micron Tesla. So do you have
Yeah,
a sense?
actually, that's a pretty big field, but that's at the location of the thing. So
10 nanometers above, yeah.
yeah, 10 nanometers above. Oh, that's maybe, then it's probably doable with an NV center, in fact. Especially if you have a way of modulating it in and out of the resonance, because then we can do an echo to do the detection. If you're just doing DC sensitivity with one NV center, you know, you get about a micro Tesla per root hertz sensitivity, and you can do better than that under some careful conditions, but that's about what it is with like a scanning probe. If you're able to apply, you know, some dynamical decoupling, which will decouple away your signal unless you can modulate it. But then you can get a significant improvement in the sensitivity. And so now you're talking about maybe 100 nanotesla per root hertz or something like that. So if you're in that range, then it's quite detectable.
That's nice. Thank you.
So as Dennis mentioned, so you can probably express this transmission in terms of two amplitudes that you add and then square to calculate your transmission. So those two amplitudes would interfere when you add and square, and that's how you get the interference. And there's a formal way to do this, you know, involving your greens. You're using Green's function. It looks like, but Dennis, this is exactly right? So I would encourage you to go back and look at this, so you understand in terms of this interfering, because that's a well-known phenomenon.
Yeah.
You know, in nuclear physics, for instance, when you send a particle into a nucleus, and then it can go in and form some resonance. That's one process, and the other process is when it just scatters off without resonance. So the two channels, usually you have to have two channels that interfere coherently. So you don't add the amplitudes squared, but you rather add the amplitudes and then you square. So the cross section has this funnel line shape. You can show it formally, and you can identify a parameter that controls whether you have a resonance or an anti-resonance. It can go all the way from, say, a Lorentzian to a inverted type Lorentzian, and in between you have this asymmetric line shape.
Oh, that's nice. Thank you.
Yeah. So they were talking about the Q, the parameter Q on the correct. So Washington did not present, but we developed like a 2x2 effective model to describe the feature, and actually the projection that he's doing is just to kind of like identify numerically what are the parameters that are going to fit in the 2x2 models. But so I know that Washington has that calculation, and I also do, and so that's exactly what we're planning to do to accurately describe what we're seeing in this black box Green's function calculation.
Thank you.
Let's thank Washington again.